Unit 2, Kinematics. Python lab for inverse kinematics. In this lab, we will demonstrate how to use Python program and functions for inverse kinematics. We will continue to use graphical methods. Example 1, cylindrical manipulator. This one, you have a rotational joint and a prismatic joint. So we are going to give you two variables, x and y. You need to find out the value of the d and theta. This is a 2 degree of freedom manipulator. So basically the model is over here. Your theta will rotate and your A2 will be attaching the prismatic joint and also the rotational joint. And this prismatic joint can extend, and there is an A3. So we are going to use this model. And the Python code is over here. Let's look at the example at the PyCharm editor. So as you can see over here, you can include the PyLab package, and you can import NumPy as NP. And your A2, A3 are 1. And here we are going to model this cylindrical manipulator. So you have a rotational joint, and there is an A2, and you have prismatic joint, and you have the extension part, and then you would have the A3 and the end effector. So this one you will rotate in this direction. So extension or not, you actually will keep the same direction over here. So basically here, we are going to have 1, 1, and then this extension, we have D. So we try to use y equals -3 to 3. So actually, it will be right here. From -3, it will down here to 3. And x is always 3. So we keep the x equals 3, y from -3 to 3. And then the r will be the distance from the end effector to the original point. And we use these two numbers to calculate the d and the theta, t for theta. So the formula we already showed in the previous lab. And here we use them to calculate the d and theta. And we can plot the d versus y. Because our x is fixed, so we use t, the theta, versus y, that will be in blue color, and d, the extension portion, versus y, that's in red color, so that's wrong. So as you can see right here, when y equals 0, is over here, it's actually at this point. Then your d is equals 1. And once y becomes 3, x is equals 3, then your r will be square root of 2 times 3. And then d will be this one minus 2. So you will go to here. Okay, let's look at the second example. In the second example, we are looking at a prismatic manipulator, degree of 2 freedom. Here, actually, we have an extension, prismatic joint, and a rotational joint. The order is different from the previous one. This one we discussed in previous lab for the formula as well. So the model will be like this. So here, because we have a D that's extendable, and we have A equals 1, A3 equals 1, A1 equals 1, and we are going to find the D and the theta. So now let's look at the PyCharm code. So over here, we import the same library, A1, A3 to be 1. And in this one, let's look at it. We have a G. G is in this direction. We keep it at 2. So this one, actually, you have a prismatic 1, and you have D, right? And this one, you have A1, and that's 1. A3, you'll be over here, right? And here you have the theta. So basically, if we are trying to have the G equals 2, so G is kept at 2. This G is kept at 2. And then x is minus 1 to 1. So it's going from here to here, 1 and minus 1. So if you are 0 degree, it will be here to here. This one would be your A3, and your A1 will be here. And then when your angle become bigger, you go this way, this way, this way, and your A3 would be like this, and your A1 would be like this, and your D will be here, here, and here. So we calculate the R. The R actually is the projection under the A3, and that's R. And we use that to calculate D and also calculate the theta. So this one, we explained it in previous lab. So let's look at the simulation result. As you can see right here, the blue one is the theta, and the red one would be the D. And the D is between 0 and 1. So we showed it very clearly. Okay, let's look at example 3. Example 3 is this one with 2 rotational joint. The calculation is more complicated. We show it in the previous slide. So here are the equations. We already talked about it in the previous slide. So let's look at the PyCharm code as well. This one we will use random simulation to show the point, because we are going to demonstrate the calculation of the thetas and phis. So we are not going to actually show you any line. So here, the package we import are the same, and A2 and A4 will be 1. N is the number of the data point. And here we define the cosine law. So here, basically, you are thinking of A, B, and the C. We calculate the theta over here. That's the theta we return for the cosine law. So given any number A, B, C, the 3 sides, and we are going to calculate the angle that actually is opposite to the side C. And this one, we actually are given N data points, and we create 2 lists, X and Y list. So here we use the random number generator to generate the point. The theory behind it is actually we are going to generate A and A, B that's within 2 minus 2 range. And whatever A1, A2 that actually can do, it will be within this range. A2, A4 that can reach, because each section is 1. So if they are straight in one line, the maximum range you can reach will be in here. But you can also basically go like this, come in here and come back. So basically 0, 0 can also be reached. Any location inside the circle can be ranged. So R equals to any location inside the circle of the radius within 2 would be okay. So we are trying to use a random number generator to generate a number starting from -2 up to 2. So we are trying to generate A in this range, also B in that range as well. And we calculate if the radius is outside this radius range, then we will actually give out a point. If it is inside, we actually will keep a point and add it to the XY list. And then we use those valid points to calculate the R and to calculate phi 1, phi 2, phi 3 based on the equation are given. And we calculate the theta 1 and theta 2. Theta 1 and theta 2 are converted into the degree scale. So something like this. So let's assume that we actually just use this scatter to look at the X and Y. And the scatter chart will look like this. And here, because we limit the A must be greater equal 0, that actually in the first quadrant. So we only consider the first quadrant. So if we don't consider the first quadrant, we consider the whole circle. You can use this one. You can comment out this line and open that line, and you can actually run it like this. You will see a circle. original plot is not to the scale, so you can pull it and you will be to scale, become a circle. So that show you that this about 10,000 points will be scattered out into our solution space. Right here, I'm not trying to predict any paths. So I'm just using the XY that I get from this random number generator to create a scatter chart. And then let's look at the corresponding theta 1 and theta 2 for these different points. And as you can see right here, theta 1 and theta 2, if you actually open other quadrant, theta 1 actually going from 90 degree to plus 90 degree. Okay, and theta 2 from 0 to pi. So that's the range you will reach. Okay, so that's the range of the theta 1 and theta 2. So be aware that arc cosine function that we are using over here, it actually is from 0 to pi. And in fact, some of the angle may be negative, because if you are considering the full circle, it is possible that you're going into this direction. Your angle may be negative. Your angle may not be positive. So the simulation with only the first quadrant actually makes sense sometimes. Okay, so here I give you some flexibility for you to choose, but the purpose is to demonstrate these different formula. And we use different scatter chart to show you how to plot the phi 1, phi 2, phi 3, T1, T2, and we also show you the scatter chart for X and Y, and also the T1 versus T2. You can comment out some of the scatter chart plotting and also activate some other one. Okay, thank you. And there will be an assignment based on these formulas. And you can use whatever formula we have here. Thank you. Bye now.